explorers, and welcome to the third video, part of our release of Luminosity. Now, I'm thrilled to be here in the Chandra X-Ray control room here in Burlington, Massachusetts, with our very own expert, Dr. Grant Tremblay. It's nice to meet you.
David, it is such a pleasure. We're so happy you're here. Welcome.
Now,
I think our first composer ever in the Chandra control room.
Yeah, is that okay? Am I allowed?
Oh, come on. Let's make this the first of many visits. As you can tell, we love our observatory. Chandra is our beloved great observatory, and so we love showing it off to folks, including musical composers. So let's make this the first of many visits.
Well, I might hold you to that.
Yeah. And hijack the telescope and observe some targets if you want.
I've spent the last 6 months of my life delving into this one image and trying to experience the richness of it. And there's so much there. I mean, it's a galaxy cluster, and that's your field. So could you tell us what are these objects?
Yeah, that's right. So galaxy clusters are the largest and most massive gravitationally bound objects in the known universe, right? So they sit at the intersection of what we call dark matter filaments. So I know that you take, images of cosmic structure and compose incredible symphonies from them. I hope one day you consider doing one from what we call the cosmic web, right?
The web.
Of which we only have simulations, right, for what we think it looks like. But really, this is this filamentary network of what we call dark matter filaments. And when they intersect, just like the intersection of webs of a spider's web, you get a locus, a gravitational meeting crossroads for galaxies, for baryons, luminous matter to fall into, form structure. And so it's at these loci, these nodes of the cosmic web, that you get the most massive structures in the known universe, galaxy clusters.
Now, are we living at one of these nodes?
Yeah, that's right. So the Milky Way galaxy, our home galaxy, is part of a local group of galaxies. And it is possible, and there's been a paper that suggests this, a big result actually, that our local group is part of ultimately what's called the Laniakea supercluster of galaxies. This enormous cosmic structure. And so, yes, it is totally possible that the Milky Way really is part of a supercluster of galaxies.
So these clusters are out there. We've got this sort of cosmic serendipity. These webs will meet, and then you get amazing structure. I mean, looking at the image, I've talked about how what you're drawn to when you look at it is these bright stars with these jagged spikes, but that's a distortion. That's the James Webb Space Telescope. Its particular hexagonal shape creates those. So you really have to look beyond into this mass in the middle. And that's the cluster. How big is it?
Yeah, so this image, which was one of the first JWST first light images that was released, as you probably know.
Yeah, so exciting.
Yeah, that's right. So when you're looking at a cluster of galaxies in optical light, which is really what this is, optical near-infrared light from the James Webb Space Telescope, you need to understand that of all the baryons or particles of luminous matter that are in this galaxy cluster, only about 1 in every 10 particles of matter are actually found in a star, right?
Okay.
The bulk of the mass of the galaxy cluster, that's not dark matter, the bulk of the luminous mass, is taken up by what we call the intracluster medium, this otherwise invisible spherical ball of hot gas, which in this case is about 2.5 million light years across. And that is observable only in the X-rays because this gas is very hot and it shines through something called Bremsstrahlung radiation, which we observe in the X-rays with Chandra.
So that's why we're here, of course, to see that while the James Webb is incredibly powerful and shows us a lot, it doesn't see these high energy X-rays.
Since the launch of the James Webb Space Telescope, the power of Chandra has only increased, right? Because JWST and Chandra, just like HST as well, are just incredible force multipliers for one another.
Right.
They are the ultimate synergy machine. So, for example, the James Webb Space Telescope and Chandra just paired together to detect the most distant known black hole, like a black hole at the very edge of cosmic time.
We love black holes here.
That's right.
Multiverse.
And it's a remarkable transformative result. A big news outlet called it one of the most transformative science results of the prior year. And that would not have been possible had JWST not had Chandra to observe alongside it.
And they're very, I mean, you can think of them about maybe like instruments of our orchestra.
That's right.
So yeah, we've got X-rays. They're sort of getting up there, almost the sort of highest frequency that we can see. So maybe, I don't know. Maybe that's the flute or the oboe.
Yeah. Well, hey, look, I'm no musician. You're the expert here, but a symphony sounds better with multiple instruments, right?
Right.
And that is absolutely true. It's like this beautiful harmony of two great observatories working together and transforming our understanding of the universe.
So we put them together and we get this wonderful blue cloud. I think, I mean, it's a little ominous that there's this giant blue structure that is in fact sort of shaping everything that's going on, and it's we call it a cosmic conductor, in that it has this hidden influence that you need the X-rays to see. So what is the impact of the cluster on sort of everything else that's in the image?
Shortly after the launch of Chandra in 1999, it started observing the most urgent, obvious targets that you would do with a high effective area, high spatial resolution X-ray observatory, and that is to observe clusters of galaxies. Because we've known since the 70s that they are pervaded by this plasma, these enormous spheres of what we call the intercluster medium.
It's hot, right?
Yes, galaxy clusters are pervaded by this hot gas, enormously hot, like hotter than the photosphere of the sun.
Wow.
And so it shines in X-rays. And so when Chandra observed, shortly after launch, these clusters of galaxies, what we noticed incredibly was that they weren't just smooth distributions of gas. It wasn't just this perfect homogeneous sphere of gas. They had enormous holes, bubbles, buoyantly rising cavities that are so large you could fit, in one case, 400 of our Milky Way galaxies in one of these buoyantly rising bubbles. And the structure of these bubbles and the way in which they uplifted what we call multi-phase or multi-temperature gas from the galaxy that these bubbles were initially born in is almost literally like a bubble that's buoyantly rising in water, right? So if you were to go underwater and blow bubbles, the way the bubble expands as it goes up in altitude, up toward the surface, the same thing happens in galaxy clusters.
But it's on a huge scale.
On a truly enormous scale, hundreds and hundreds of our own galaxy could fit in these bubbles. So what is this? These are bubbles that have been blown by a supermassive black hole at the very center of the centermost galaxy in this galaxy cluster.
Right in the middle of
right in the
image.
center. Yeah. So these are, let's get the size scales right. A supermassive black hole is at the center of this central galaxy, which we call the brightest cluster galaxy. For a billion solar mass black hole, the size of the event horizon is about the size of our solar system, right?
So that's a billion times the mass of the sun.
Yeah, a billion times the mass of the sun. There's a mathematical boundary that we draw around black holes called an event horizon. It's called the Schwarzschild radius. So
if you go beyond that, it's curtains.
Yes, this is the boundary at which you have this point of no return, right? But so the size of that event horizon for a billion solar mass black hole is about the size of the orbit of Neptune in our solar system. So it's about the size of the solar system.
So yeah, a size that we have some comprehension of.
Exactly. Yeah, definitely big, but comprehensibly big, right?
Yeah.
And these supermassive black holes launch these bipolar, like bidirectional jets of plasma that propagate initially near the speed of light, relativistically.
We've ridden those jets through music.
That's right. Okay, that's great.
The Hercules jets.
Okay, exactly. Herc is a beautiful example. And these jets, as they propagate outward from the galaxy, push aside the ambient plasma that this galaxy is sitting in, almost like a truck plowing a snowy street, right? And the snow plow piles up and creates a cavity in the snow, right, as it moves. The same thing happens with this plasma as it's propagating. And then these bubbles are excavated or blown almost by these relativistic jets that travel through, and then they decouple and then buoyantly rise.
So that's why it's not a perfect circle.
Exactly.
That's why it has. I mean, that shape was so interesting for me. I used that to make the bass line for the song, and if it was a perfect circle, it'd be super boring. Wouldn't have
there's structure. Right?
Wouldn't have the same music. For music, we need order and chaos coming together, and that's why the universe. Well, that's where it all comes from. I mean, I love looking at the sort of the top left of the image. It gets very chaotic.
Yeah.
So I guess that's we have the black hole to thank for that.
Yeah, so in many of these clusters, this supermassive black hole is creating structure in this big ball of plasma that is many, 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 many orders of magnitude larger than the black hole itself. So, to give you a comparison, if you imagine that supermassive black hole is the size of a grape, the region, the volume that it impacts, that it orchestrates, that it conducts, if you will, throughout the intercluster medium would be relatively the size of the Earth. So imagine something the size of a grape or a quarter in the United States.
It's punching above its weight.
Punching vastly above its weight by about 1 billion-fold contrast in scale. And that is how powerful these supermassive black holes, or really the matter falling into them. As matter falls into them, they liberate an enormous amount of energy, and that energy has to go somewhere. And it's remarkable how much that relatively small black hole can dictate and drive and orchestrate the evolution of the galaxy that it's sitting in and the cluster as a whole.
And we're here to perceive it and to understand, which, I mean, I just find it so moving that we're just in the last few decades. I mean, Chandra in the 90s, we're gaining this eye on the universe, but this understanding of the underlying order that it's been a quest of humanity since the beginning, and here we are. I definitely think we don't appreciate it enough, and for me, it makes me want to make music, and for others, well, I hope we can all, channel it into our lives. So we've revealed the circle. So I guess it's not a perfect circle, and this is all X-rays and infrared. These photons. Now, what's gravity doing in this image?
Yeah, gravity is binding it all together, right? Gravity really is the curvature of space-time itself, right?
Yes.
And Einstein's theory of general relativity.
It's still holding up?
It's still holding up, and it sounds really fancy. It sounds really fancy, pages of equations, but really, ultimately, all it says is that mass tells space-time how to curve, and that space-time, by its curvature, tells mass how to move. So what do I mean by that? You and I are both warping space-time right now, right?
Yeah, maybe a little bit more.
No, come on. But the more massive the object is, the more it warps space-time, right? So the Earth is warping space-time, our sun is. And as you get to massive clusters of galaxies, they are, like I said, the most massive objects in the known universe.
There's some good pull there.
Yeah, and so they are an absolute, not just a valley, but an enormous depression in the fabric of space-time itself.
A Mariana Trench.
Thank you. That's perfect. Yeah, and it's hard. Look, we have to picture it as almost a two-dimensional or at best a three-dimensional thing, but this is
another dimension.
Yeah, that's right.
Well, we can model it. Yeah, we don't have a way to see it with our eyes. The eyes are.
Well, look, I'm glad you're here because Chandra has been our front row seat to the symphony of the cosmos. What do I mean by that? For example, there's a galaxy cluster. Maybe, you can show it on the screen. That is where Chandra has observed these ripples in the intercluster medium, ripples in the plasma across millions of light years. And you can measure the frequency, really, the wavelength of the frequency of that literal sound wave, right? So it's creating...
traveling from you to me. But this
exactly. I'm creating matter compression waves right now through the air as I'm talking to you.
Through.
That's why your audience can hear this, because your speakers are creating matter compression waves that are bouncing and vibrating your eardrum. These matter compression waves in this intercluster plasma are the lowest known musical note in the universe, a B flat, 57 octaves below middle C. Right? Can you play that on a violin? I'm not a musician.
Yeah, I think we'd have trouble even on a tuba or a subwoofer. Yeah, we'll see. Well, we want to shout out to Matt Russo, Andrew Santiago, the team that made that. That's famous amongst us science musicians. That's Sonification, who the System Sounds project, who made that. Inspired us all that there's real sound and music out there in the universe to be enjoyed.
Absolutely, yeah.
So that's a black hole making music, and what else are we going to find?
Look, galaxy clusters are cosmic telescopes. Because they warp that fabric of space-time, they are acting like a literal lens, quite literally like a glass lens, which, technically changes the index of refraction, and that's why it focuses light. The same thing is happening from space-time itself. So if you imagine a big cluster of galaxies, objects behind it are going to be magnified. As their light passes through this warped space-time, it'll be magnified. And the observer here, us here on Earth,
that's us, yeah.
are using this lens as a great cosmic telescope. So we can use galaxy clusters as a telescope to observe incredibly distant objects far back in cosmic time that we would not otherwise be able to observe.
Now that's these red sort of streaks, and these. I had a lot of fun sort of picking these out, and they even if you don't have the Chandra blue data, you sort of see, if you spend some time, they're forming this circle. But it's not a real circle, right? It's kind of it's a distortion.
That's right. So the deformation of space-time has structure to it, right? This is not a perfect sphere, right? And so it's kind of like looking through the base of a wine glass. If you do this, and you could do this right now, do it in your home. And you'll see the distortions. And of course, the base of a wine glass isn't perfect, right? And so there are imperfections.
Yeah.
And so the way it's distorting the light you're seeing through it is kind of like how a galaxy cluster works. So that's why you get these multiply lensed images sometimes.
So there's a cosmic wine glass being held up to this image.
Yeah, basically, kind of, yeah.
That's how big is that wine glass? 2.5
million light years across.
Decent.
Yeah, so that's a cup of wine, yeah. That'll put you to bed. That'll
get you through Christmas with the in-laws.
That's right. Not my in-laws necessarily.
So then everything we're seeing is being bent and warped in some really interesting ways. Is that just annoying then that we have to kind of correct for that?
No, it's incredible. Look, it's incredible. I'm so grateful that the universe works this way, because it not only allows us to see in the distant universe, it allows us to look to the edge of time itself, right? So one thing your viewers should understand is that looking through space is the exact same thing as looking through time, right? Mm-hmm. So you have never actually witnessed the present in your entire life. You're sitting about 2-3 feet away from me right now, right? Light travels at about 1 foot per nanosecond, 1 foot per billionths of a second,
so
right?
So we got few nanoseconds.
Yeah, you're seeing me right now because the ambient light of the room is bouncing off of my face, and some fraction of those photons, those particles of light, are bouncing directly toward your eyes. But it takes time for that bounced light to travel from me to you. And in this case, it takes about 3 nanoseconds. So you are seeing me right now 3 nanoseconds in the past.
Not sure my brain can handle that.
Yeah, and if I were to step another foot away from you, you'd be seeing me 4 nanoseconds in the past. And if I were to go a light year away from you, you'd be seeing me as I was 1 year earlier, a younger man. And so the time travel is real. It's the same thing as looking through space. So when you can use a massive telescope to see further away, you are also seeing further, deeper back in time, closer toward the beginning of time itself.
Further and further. Right. So how far can we see?
Yeah, well, look, on Earth, we want to build as big a telescope as possible, right? 30-meter telescopes on the ground, as big a space telescope as you possibly can. But there is no telescope that we could ever build that is bigger or more powerful than a galaxy cluster, right? Sorry. And so these galaxy clusters, like SMACS 0723, is such an incredible opportunity to observe the universe behind it. We've observed a redshift 10 black hole. This is a black hole at the edge of time itself with Chandra and JWST, only about 400 million years after the beginning of time itself, right? So billions and billions of light years away. We've observed a star called Earendel, which...
Oh, yes. Yeah. That one's beautiful.
The most distant known star ever observed, right? An individual star magnified by almost 40,000 times.
But not the first, right?
Not the first. There was an earlier one, that's right.
Well, I mean, the very first star.
Yeah, it's definitely not the very first star in the universe, right? Well, for sure. We can't see quite that far back, right? But that's right.
Yeah, well, it's a tantalizing prospect for me, kind of. I mean, people know I'm a musician, but I've, spent the last few years really immersing myself in, there's news breaking all the time in astrophysics, and it seems like the discoveries are just keeping coming, and what a time.
Look, our knowledge of the universe is best defined by all that we don't know, right? In some ways, my job, and I'm an astrophysicist, my job is to be slightly less wrong every single day and every single year, right? But I have no doubt that there's some fundamental paradigm in our understanding of the universe that will be shown to be incorrect, whether it's tomorrow or 10 years from now or a century from now, right? 150 years ago, the world's smartest people thought the universe was permeated by something called the luminiferous ether, right? This ether that permeated everything. And then a simple experiment, a really, really, kind of low-tech experiment showed, oh, no, that paradigm is totally wrong.
Right.
And so one thing I love about astronomy is that the discovery literally rains from the sky, right? And all you have to do is collect these photons. So we have to do this in space with X-rays, right? But it's an extraordinary field because yes, the discoveries come every single day.
What a time! And if we can all become part of that, I mean, I find it so fulfilling as a big science nerd, basically, a science fan.
Well, David, I have to thank you. So I've attended your symphony. I was just blown away by it. But what your work did is so I look at, Hubble and James Webb and Chandra images of galaxies and galaxy clusters every single day. And when you do it every single day and it's kind of your day job, you kind of
another galaxy.
Yeah, you kind of lose the match. Sometimes I have to remind myself that this Hubble image of a galaxy could have 10,000 advanced alien civilizations in it for all I know, right? Wow. But what your work has done is give even us fuddy-duddy professional astronomers a new look at our own data, right? And hearing as you move around some of these images and hearing your symphony play as it moves around is another way of viewing the universe, but hearing the universe.
To experience it. Sound has got this ability. It gets through your filters. I don't know. We're bombarded by light.
That's right.
By commercials and stuff.
That's right. There's so much signal nowadays.
Yeah. Sound. I don't know. We get straight to the heart.
Yeah, it makes you feel more part of it or inside of it than just a two-dimensional image does.
But we're going to keep working to help immerse people, and if we can inspire the astronomers to keep their amazing work going, then that's all for the better. So what's next? I mean, Chandra, 25 years.
Yeah.
We must be preparing more telescopes and. Yeah, what's on the horizon, Grant?
So look, Chandra has a lot of life left to it. It is doing its best of mission science.
Yeah.
It is maximally relevant, and its relevance is even growing every day, especially in our new golden age of multi-wavelength astrophysics with 30-meter telescopes coming on first light on the ground, James Webb Space Telescope, something called the Nancy Grace Roman Observatory. And we are also headed into something what will really be a golden age of time domain astrophysics, and that you can think of the sky as some static, unchanging thing. Right, but in fact, the sky above you at all times is going boom, bang, and flash at basically every single time scale, from nanoseconds to giga years, right?
And so we could see it.
Yeah, I know, right?
Perceive it.
Well, Chandra will be a keystone instrument in our looming golden age of time domain astrophysics because it will enjoy enormous synergies with something called the Rubin Observatory, which will take a movie of the sky every couple of nights. The Vera C. Rubin Observatory, first light in about a year from now.
Coming up.
Yep. And the Nancy Grace Roman Space Telescope, which will launch in 2026. And so Chandra has a lot of life left to it, yes, but of course, all missions end. We hope that that's a long time from now for Chandra. It has more, potentially almost a decade of really great science remaining. But we're always looking toward the future, including something called the New Great Observatories, which is effectively a top recommendation of one of our prior so-called decadal survey. This is the National Academy's report that advises the nation on where to invest U.S. taxpayer dollars in engines of cosmic discovery. So the first New Great Observatory will be called the Habitable Worlds Observatory.
But those exoplanets.
Yeah, that's right. Yep. And it's going to be extraordinary. Check out habitablewordsobservatory.org. But I also want you to check out greatobservatories.org because that will show you the full vision of what this fleet could be, which includes, yes, the Habitable Worlds Observatory, but also a successor to Chandra called the Lynx X-Ray Observatory.
Okay, more X-rays, more detailed.
Lynx will build on Chandra's legacy by being orders of magnitude more powerful than Chandra across multiple dimensions, right? 1,000 times the spectral resolution, hundreds of times the sensitivity, spatial resolution that is incredibly sharp spatial resolution across a huge field of view. So you can survey the sky 800 times faster than Chandra. Wow. So look, Chandra has been a revolutionary instrument. It continues to be to this day. And frankly, will be the greatest X-ray observatory in history until a Chandra-like successor can fly.
Which might a little bit of a wait to go from.
Look, you know, the future's hard to predict. Mm-hmm. Things can be, you know, take forever, and things can happen a lot faster than you think. And so we hope it's the latter for Lynx, because I want to see one day a successor to Chandra fly.
Well, we'll keep banging the drum. I mean, we have so much to be grateful for. This flood of light and discoveries, magic and music of the cosmos enriching our lives. Yeah, I feel privileged to be part of it. And, well, let us know what you think of anything in the interview. Myself or Dr. Tremblay will be happy to answer questions. And you can see more of these Voice of the Universe projects in the new year. Actually got a few ideas for what we can do next.
Okay, great. Yeah.
From this conversation. Yeah, so inspiring. Thank you so much,
Thank you,
Dr.
sir.
Tremblay.
Welcome here anytime.
Thank you.